First of all, I'd like to thank organizers for giving me this opportunity to introduce our activities. In this talk, I will describe our current activities towards integration of simulation data learning and preparations for next operations system, Oakforest-PACS II. I'm a faculty member of the Supercomputer Center at the University of Tokyo. This is the history of our systems. Recently, we have more systems with accelerators, such as GPUs, and this continues in the future for a while. These pie charts showed research areas of our systems based on machine hours in 2020. In CPU systems, computational science, such as simulation in engineering, earth and space science, and material science are the typical applications. These are the traditional areas of usage for our systems in recent 55 years. On the contrast, workloads on GPU clusters are very different. Large portions are occupied by information science related to artificial intelligence and bioinformatics, and such as genome analysis and medical image recognition by machine learning. Supercomputing is changing now. We have new types of workloads and users related to big data analytics, AI, and machine learning, in addition to CSE for simulations. Integration and convergence of simulation, data, and learning, S+D+L, is important towards Society 5.0, proposed by Japanese government, which is a super smart and human-centered society by integration of cyberspace and physical space. Since 2015, we have been developing a new platform for integration of S+D+L, which is called BDEC, Big Data and Extreme Computing. We are focusing on S. Our approach is based on AI for science or AI for HPC. Wisteria BDEC 01 is the first BDEC system, which is a platform for integration of S+D+L. Peak performance is 33 petaflops, and aggregated memory bandwidth is 8.38 petabytes per second. This system is constructed by Fujitsu. Operation started on May 14, 2021, and it is a hierarchical, hybrid, and heterogeneous system with two types of node groups. Simulation node for HPC, it's an Odyssey, with more than 25 petaflops based on the Fujitsu Prime HPC FX1000 with A64FX with high bandwidth memory. And this part is a commercial version of the Fugaku supercomputer. Data and learning nodes, Aquarius, a GPU cluster consisting of Intel Ice Lake and NVIDIA A100 Tensor Core with 7.2 petaflops for data analytics, AI, and machine learning workloads. Some of the data and learning nodes are connected to the external resources directly, and it has totally 360 A100 GPUs. This is how we utilize the Wisteria BDEC 01 system for integration of simulation, data, and learning. Models and parameters for simulations are optimized by data analytics and machine learning. That we can accelerate the procedures for parameter studies in real-world nonlinear simulations. These pie charts show the ratio of machine hours in 2022 for each of Odyssey, Aquarius, and Oakbridge CX, OBCX. So OBCX is a mid-range cluster with Intel Xeon Cascade Lake CPUs. Aquarius with A100 GPU is used more for AI and bioinformatics than any other. This is the first half of this fiscal year from April to September 2023. Colors in the pie chart of Aquarius are also very different from others. In the last 6 months, more than 25% of Aquarius was spent on AI workloads due to a special project on large language models. OBCX retired in the end of September. H3 Open BDEC is an innovative software platform for integration of S+D+L on the BDEC system. It is a 5-year project supported by Japanese government since 2019. Leading PI is myself, and total budget is $1.4 million for 5 years. And this year is the last fiscal year. Collaborators are specialists of the computer science, high-performance computing, computational science, numerical algorithms, data science, and machine learning. And this is a list of the international collaborators. We have three significant innovations in H3 Open BDEC. One is innovative method for numerical analysis, which is based on the new principles of computing by adaptive precision, accuracy verification, and automatic tuning. We are investigating the utilization of mixed and low precision computing. Another innovation is integration of simulation plus data plus learning by hierarchical data-driven approach. We also have the third pillar of this project, software and utilities for heterogeneous environments, such as Wisteria BDEC-01. So I'll talk about details of this part. Because the Wisteria BDEC-01 is a heterogeneous, a single MPI job over Odyssey and Aquarius is impossible. Actually, they are connected through InfiniBand EDR with 2 terabytes per second. So we developed the communication procedures with H3 OpenSys Weight IO socket. It's a library for inter-process communication with MPI-like interface. So this is the API for the communication library, Weight IO socket. Its interface is very similar to that of MPI, and it can be easily called from programs written in C and Fortran. We are also developing a new coupler, H3 OpenUtil MP, which combines Odyssey for simulations and Aquarius for AI machine learning through InfiniBand EDR. This coupler was originally developed for a homogeneous supercomputer system using MPI. This is now working on heterogeneous environment, such as Wisteria BDEC-01, using Weight IO socket. This slide overviews 3D earthquake simulation with real-time data observation and assimilation. We utilize real-time observation data, including satellite data of JDX-net, with 2,000 observation points in Japan through SciNet, which is a Japanese academic network. In traditional approach for seismic wave propagation, simulations are pure simulation or pure S. We assume source terms for initial conditions at epicenter. Actually, estimation of the source terms and the initial conditions is very difficult. So if we specify wrong conditions, results of simulations are inaccurate. In the new method, by integration of data assimilation and simulation, it's a A+S. We do not need such source terms and initial conditions. Initial conditions are generated by interpolation of real-time observation data as yellow triangles. Results of simulations are collected using real-time observed data by data assimilation. In the present work, we apply very simple assimilation method called optimal interpolation technique. Computing is starting from A+S and switching to pure simulation at certain timing. We are using same mesh model for A+S and pure simulation. So these procedures are proposed and developed by my colleague, Professor Takashi Furumura. He's a Earthquake Research Institute of the University of Tokyo. So this is a system for earthquake simulation combined with real-time data assimilation on Wisteria BDEC-01 using Weight IO library. Aquarius is doing filtering and visualization, while Odyssey is doing simulation and assimilation. This slide shows code written by Fortran calling Weight IO library. Aquarius is sending the result of filtering, and Odyssey receives the data. The system was evaluated by Niigata 2007 earthquake with long period wave. Each edge length of the cubic mesh is 240 meters. We have total 900 millions of meshes, which covers 46 kilometer square region of Kanto area in Japan. We have more than 350 observational points in this target area. And the yellow star is the epicenter, and red triangle is the observation point in Tokyo. We compare the observation and computed result at this point. So this is the result. The graphs in the right-hand side compare effect of switching time from A+S to pure simulation at point in Tokyo. This movie shows the result for switching at 70 seconds. You can see that if the switching occurs after 50 seconds, simulation agrees with observation well. This slide shows an example for atmospheric simulation of clouds by my colleagues, Dr. Yashiro and Dr. Arakawa. This simulation includes two parts. One is high-resolution model for detailed simulations. Another is coarser model for parameterization. This time, we replace the coarse model for parameterization with AI. So this part requires 25% of the total computation time. Okay, like this way. In this machine learning procedures, air density, internal energy, and density of air, water vapor are the input, and the gradient in time direction is the output. PyTorch is used as a framework for machine learning on Aquarius, and multi-layer perceptron with 3 layers was applied. It's a very simple model. Okay. Left-hand side is the input, middle is the output by simulations, and right-hand side is the output by inference. Generally, simulations and AI agree well, but the reproducibility of extreme values needs improvement. This slide shows how to run such workloads on Wisteria BDEC1. So currently, one node of Aquarius is reserved for such computations. We need to submit 2 separate jobs, and more flexible and maybe complicated policy for scheduling is needed. Okay, so let's go to the second part. Next, I will describe our plan for the next generation system. JCHPC, Joint Center for Advanced High-Performance Computing, is a collaboration between University of Tsukuba and University of Tokyo since 2013. We introduced a big system by combining budget of 2 supercomputer centers and Oakforest-PACS OFP with more than 8,000 Intel Xeon Phi is the first system of JCHPC. At the first appearance in the top 500, November 2016, it was 6th in the world and top in Japan. After retirement of the K computer in 2019, OFP worked as a natural flag system, in fact, until operation of Fugaku starts in 2020. OFP retired in March 2022, and we are now preparing for a successor of OFP, the OFP-II. In order to attain maximum performance under constraint of the electric power consumption, switching to accelerators such as GPU is essential in next 10 years. As you know, after February 2022, energy cost has been increasing and the cost of electricity was doubled, while this is now stable and reducing. OFP-II will start its operation in January 2025. It consists of 2 types of node groups. Group A with general purpose CPUs only, and Group B with GPUs. We continue the direction for integration of S+D+L. We also introduced Mercury system, prototype of OFP-II, this October. So actually, we have already decided the architecture of GPU in June 2022, more than 1 year ago. Okay? We need to prepare for the porting codes of more than 3,000 users of OFP to GPUs. And we estimate we need 18 to 30 months for that. Selection was based on the 7 benchmarks in the next page. So these tables summarize the 7 benchmarks. All of them are traditional simulation code for computational science and engineering, and 4 were written in Fortran. So finally, we adopted NVIDIA's GPU, which is a H100 or its successor. Performance itself and portability of the application in Fortran are highly evaluated. OpenHCC and standard parallelism are relatively easy and are suitable for existing applications by users with MPI OpenMP hybrid. We released our RFP of OFP-II in late August this year, and we expect peak performance of the Group B is more than 100 petaflops. CPUs in Group A and Group B could be different. Moreover, we start operation of Mercury with 16 H100 in late October. Next page describes the detailed plan for porting. These activities are done under strong support by NVIDIA Japan, so thank you very much. Because we have more than 3,000 users, we have 2 categories for support. Generally, we recommend the users to port their application to GPU by themselves. We have many options, such as 1-week hackathons every 3 or 4 months, both of the online and in person. Monthly open meeting for consulting via Zoom, and excellent portal site with useful information. So this is a entrance of the portal site. So I'm sorry, it's in Japanese. We have another procedure supported porting. So we are supporting 17 groups of community calls and open hall. While we also prepare special budget for outsourcing, many members of these groups are also attending hackathons. Mostly, our users' codes are parallelized by MPI plus OpenMP. Therefore, OpenACC is recommended. So this table summarizes 17 codes, and half of them are earth science applications. And moreover, so most of the 17 codes are in Fortran. Okay, so I will introduce several activities for porting. LINX is a simulator for cardiac electrophysiology by Simula Research Laboratory in Norway, so our collaborator. So it solves 3D diffusion reaction equations by finite volume method. The most expensive procedure is conjugate gradient solver for large-scale linear equations. Our goal is to develop a GPU version using OpenACC and standard parallelism on Wisteria BDEC Aquarius with NVIDIA A100 GPUs. As you know, applying OpenACC and standard parallelism is very easy. Just replace the OpenMP directives like this way or this way. This page describes the strategy. Basically, we replace the OpenMP part with OpenACC and standard parallelism, while matrix access is changed to column-wise structural array manner. As for the hero exchanges, we prepare the special function with CUDA aware MPI. So this function can be utilized for other applications. In the next two pages, results of best cases are shown. So this is the performance of the conjugate gradient solver. Significant improvement of performance is attained by GPUs. OpenACC and standard parallelism are competitive, while standard parallelism is worse for smaller data with more GPUs. The reason is that standard parallelism cannot launch GPU kernels asynchronously. Performance of GPU is much better for larger problems. This is a relative best performance compared to that of the with 2 Xeon CPUs. Performance improvement by GPU is significant for larger problems. Speed up is reasonable considering the ratio of memory bandwidth, because this is a memory band application. So this is a relative best performance compared to that of the, So in this case, changes are applied to less than 4% of the entire code. So next one is a Mutsu T3 MHD code with 3D FFT. The code was developed by Professor Mueller's group by National Institute for Fusion Science. Effects of the QFFT and communication computation overlapping are significant. And finally, we have attained a 13 times speed up with 4A100 GPUs compared to a single node of Xeons. So last one is the front row blue, a CFD simulation code by FEM. The code was developed by Professor Kato's group in Institute of Industrial Science in the University of Tokyo. So this is a typical memory bound application with a sparse linear solvers. Because loop structure is very simple, we just inserted OpenACC directives. And this is the performance improvement. The original code was fully optimized for Fugaku. And the performance improvement with 44% is reasonable if we consider the ratio of memory bandwidth. Okay. So this is a summary of this talk. I described our current activities towards integration of simulation, data learning, and plans for OFP-II. We are really looking forward to the installation of OFP-II in January 2025. Our goal is long but straight, not winding. Thank you very much for your attention.